We'll now review the elimination method for solving a system of equations in two variables. Step 1, we want to rewrite each equation with its variables and constants aligned vertically. Oftentimes, the equations will already be written in this form, but if not, you want to rearrange them so all the x's are lined up, the y's, the equal signs, and the constants. Step 2, if necessary, multiply one or both equations by a number so that the coefficient of one of the variables in one equation is the opposite of the coefficient in the other equation. So for instance, if one coefficient is a 5 on an x, then you want the other x term to have a coefficient of a -5. Step 3, we add the equations to eliminate one of the variables. As the method suggests, elimination method, we want to eliminate one of the variables. Then in step 4, we can solve the resulting equation for the value of the variable. So you get one of the variables first, either the x or the y or the a or the b or whatever, and then we're going to just substitute. So now, from here on, it's just like substitution. We just substitute that value back into either of the original equations to solve for the value of the other variable. And then we know finally step 6, we have to check the ordered pair solution in both of the original equations to verify that it satisfies both of those equations. So let's go right to an example, example 3. Let's solve this system using the elimination method. We have 5x plus 2y equals 1, x minus 3y equals 7. So this is already aligned. The x's are aligned vertically, the y's are aligned, the equal signs, and the constant. So we don't have to do any arranging. Now we want to look at one of the variables and the coefficients. So for instance, if we look at the x's, the coefficient of the x in the first equation is 5, and here it's a 1. So we can easily multiply our second equation by a -5 in order to get that opposite coefficient on the x. So I like to rewrite the whole system. So I'll rewrite my 5x plus 2y equals 1. And now when I multiply the -5 on the second equation, I get -5x plus 15y equals -35. Don't forget to multiply that -5 to both sides of the equation to keep the balance. Now I add vertically, I add down the columns, I add my like terms, so I've got 5x and -5x. So as we would expect, as we hope, those x's are eliminated because they add up to 0. So now I can add my y's, 2y plus 15y, so we get 17y, and then we add the constants on the right side, 1 plus -35 will give us -34. So now we have an equation with just one variable y, and we can divide both sides by 17 to give us y equals -2. Then once you have one of the variables, you can just substitute back into either of the original equations to get your other variable. So if we look at the two equations, the originals, in the second equation that x doesn't have a coefficient in front. So it would be easier to solve for x in the second equation, although it has to satisfy both. But I'm going to choose that second one since there's no coefficient on the x. So I'll substitute back in. So I have x minus 3 times -2 for y equals 7. So that gives me x plus 6 equals 7. And then we subtract the 6 from both sides, and I get x equals 1. So my ordered pair solution here appears to be 1, -2. So then we just want to make sure we check in both equations and make sure it satisfies both. So I'll substitute into the first equation 5 times 1 for the x plus 2 times -2 for the y equals 1. So that gives me 5 plus 2 times -2 is -4. 5 plus -4 does give us a 1. So that works. Then the second equation, I put the 1 in for the x. So 1 minus 3 times -2 for the y equals 7. So then 1 minus, then we've got minus minus, so that really becomes plus. 3 times 2 is 6, and 1 plus 6 is in fact 7. So that does check.